take a look at arc length of a curve. So the good news is if you are a graduate of Calc 2, you actually already saw the arc length formula, the parametric version, in 2 dimensions. Now, if you forgot, don't worry, because I'm going to review it right now for you. Yeah. Okay, so recall from Calculus 2, when you were studying parametric equations, if you've got a curve represented by x equals f of t, y equals g of t, which you can also just stick into a vector valued function, and it means the same thing. The vector valued function with components f of t and g of t. The arc length of that plane curve, so this is 2D, on some interval where time goes from a to b seconds, is given by this formula. Ooh, I forgot that one. And if you forgot, don't worry, here it is again. So you're going to integrate from a to b, and it's the square root of the sum of the squares of the derivatives of f and g. Now, let me remind you that r prime, if r is given with components f of t and g of t, r prime would have components f prime of t and g prime of t. And you should already kind of be aware of that from our study of derivatives of vector valued functions. Okay, so what? And we all know also that this is the velocity vector. And we also know now that velocity vectors are always guaranteed to be tangent to the position curve that it's associated with. Fine. So how does this help me with this arc length formula? It still looks crappy. Don't worry. I claim that what you're seeing in this integrand, the square root of the sum of the squares of the velocity vector, is simply speed. And remember, we define speed as being the magnitude of the velocity vector. That's right. So this is really cool. What we're saying is that the arc length formula is pretty easy to remember because you're going to integrate on some interval that hopefully they give to you, speed. So let's look at the 3D version. If you take this 2D version that you learned from your Calc 2 class and just extend it to 3D, voila, you've got the arc length in 3D. Yeah. So you've got a vector valued function given by f of t, g of t, h of t now, and you're looking for the arc length on some interval time going from a to b seconds. Okay. The arc length is s is equal to the integral going from a to b and this big old square root. But remember that that is simply the magnitude of the velocity vector that you're integrating with respect to time. That's just speed. That's all it is. Cool. Okay, so we're going to do a couple examples here. Example 4 is kind of easy peasy. That's why I start with it. See, when you're trying to integrate speed, you might get something that's not even integrable because it's so yucky. Okay, you know, sometimes radicals are like really bad. And I don't want us to have to do any trig sub in this class. So good news, I know you're all graduates of Calc 2 and you supposedly learned how to do trig sub as one of those integration techniques. We try to stay away from that here in Calc 3. Some other techniques I like you to know, like you should know integration by parts, you know, in the arctan rule and stuff like that, but I don't want to do any trig sub, okay? All right, so how do you get the arc length for this curve? And I think this is another one of those helix type curves. And as long as time is going from 0 to 2 pi, fine. Step 1, find r prime. Because if you're going to integrate speed, you need to go get velocity first. Okay, so the integral of 2t is 2. The integral of 3 sine 2t using the chain rule, I believe 3 times 2 is 6 cos 2t. And then again, using the chain rule to differentiate 3 cos 2t, you'll get negative 6 sine 2t. Okay, there's your velocity vector. And let's go get speed. Like, what is the magnitude of the velocity vector? Let's just see if we can't look at that baby. That's going to be the square root of the sum of the squares Oh man, I can't write today. Feels like it's Friday. Yeah. Don't distribute a radical over a sum. Here's what I don't want to see. Okay, people? If I see people going like this, da, 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 la, 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 I will be really upset. That is not legal mathematics. Well, it works sometimes. No, it never works. Don't do it. Okay, so what can you do? Well, anything legal, I'm okay with. So I'm just cleaning up these squares. Okay, now what? Anything simplify out that you can see here? Or should I just leave it or what? The last two terms have a common factor of 36. And so if you factor out the 36, you will get a cos squared of 2t plus a sine squared of 2t. And that adds up to?
1.
And so really, you're just taking the square root of 4 plus 36, which is square root of 40, and clean up this a little bit because 40 does have a factor that is a perfect square. 4, I know, not that big. So when I simplify the square root of 40, it's 2 square root of 10. Now what? Well, now you're ready to set up the integral for Arclength. Yeah, because you got your speed, and now you just integrate speed. So S, little s, is tradition to represent Arclength in every single calculus book. Okay, so don't go, oh, I'm just using S because it feels good. No, every single calculus book known to man. Arclength is denoted with little s. Little s, you're going to take the integral, and they wanted us to have the limits of their integral be 0 to 2 pi, and you're going to integrate speed. In this case, speed is just a constant. Does that always happen? No, we got lucky. Because now this is really easy to integrate. We're just going to get 2 square root of 10, and then we'll have t, and we'll evaluate t going from 0 to 2 pi. And so make sure you substitute in your upper limit first, and then you can clean this up a little bit. 2 times 2 is 4, pi square root of 10. This is the exact answer. If they ask you for the exact answer, give them 4 pi square root of 10. Now, if they ask you for an approximate answer, that means you can whip out the calculator and get some decimal approximation. Okay, but if we were looking for exact answer, it's this one here. All right. That ends that example. Not too bad. Now we're going to look at a classic. What I love about this last example I want to go over here for you is the fact that you have to know how to differentiate well and algebra issues that come into play. So what do I mean? Well, the product rule. I'm really into the product rule. I don't know if you've noticed this, but I'm really into the product rule. Like I put something like that on your quiz. Yeah. Do you think that's going to show up in a future quiz or exam? Probably. You should know how to do the product rule. That's key. So what do I mean? Well, if I'm going to go try to find the arc length of this vector value function between t equals 0 to t equals pi halves, I got to go get the derivative, and then I got to go get speed, and then I'm going to integrate speed. Okay, so first up, derivative. Now, how do you take the derivative of sine t minus t cos t? The t cos, you're going to need the product rule. So let me remind you that if you are given a product, say f times g, and somebody says, hey, take the derivative of that product, you have to apply the product rule, f prime g plus g prime f. Yeah, that's key. Know this. I would memorize it because it's important. So the way I'm going to take the derivative of the first component very carefully, and you may choose a different thing. First, I'll take the derivative of sine t because that doesn't need a product rule. That's just cos. And then minus, and I'm going to put in brackets here because now I'm going to go f prime g plus g prime f. And so for me, the t will be the f factor and the cos will be my g. Okay, here we go, f prime. Derivative of t with respect to t. I believe that's just a 1 times your g, but that's your cos, and then plus g prime. So the derivative of cos is negative sine times your f, which is still t. Now distribute this negative over the brackets and notice what happens after you distribute your negative. You've got a negative there, so that'll end up being a positive. And yes, you can cancel the cosines because they're gone. So the first component just ends up being simplified with t sine t. That was convenient. Okay, so we're done with the first component's derivative. I told you this was a little involved. Now let's take a look at the second component. Aha, we got cos plus t sine t. So I'm going to have to use the product rule again on that second term. Can you use the product rule more than once? As many times as you got to use it, okay? So when I start in taking the derivative of that second component, the derivative of cos is minus sine plus, and now I'm going to go f prime g plus g prime f. I don't have to put brackets here because I don't have a minus to distribute this time. So the derivative of t is 1 times sine t plus the derivative of sine t is cos times t. And while we're here, let's just take the derivative of that very last component. This is easy. The derivative of t squared is just 2t. And then you'll notice when you're cleaning up that second component, minus sine plus sine, hey. And so all that's left is t cos after simplifying. Well, that's really convenient. We like that. So now what? We're done getting the derivative. Fantastic. Now we're ready to kind of put everything in motion. Arclength S, which is the integral going from A to B of the magnitude of velocity, also known as speed. So for us, it's going to be 0 to pi halves because they told us that's the integral. And you're going to take the square root of, this looks like it's going to be a mess. Is this even going to be integrable? If it isn't, we can always use our graphing calculator where we use one of the features on there that allows us to take definite integrals. But I'm hoping I don't have to do that, where I can just do this by hand. And it turns out we're going to get lucky. Not always do you get this lucky, but check it out. The first two terms have a common factor of t squared. So if I take out the t squared from the first two terms, aha, that other factor is sine squared plus cos squared, and we've seen that before. That adds up to 1. We're not done though. You still have to add up t squared with 4t squared. Okay, that's not bad. That's like terms. So I just get 5t squared. And then you keep going until you run out of room. And you're going to use a pre-calc fact, little known pre-calc fact, that when you take the square root of something squared, like x squared, you're going to get the absolute value of that. So let's keep that in mind here. Eyeballs right here. Because sometimes that can come and bite you, especially doing Arclength problems. So when I simplify this square root of 5t squared, I could rewrite it as square root of 5 times square root of t squared. That's legal. And the square root of 5 is just a constant multiple, so I can pull that out front of the integral. That's legal. And then here I have absolute value. I don't know how to integrate absolute value. Seriously, I don't. You can't. So what you have to do is you have to look at the interval that you're integrating on. And lucky for us, if you graph y equals square root of t, it looks like a V shape. And on the right side of that V, 0 to pi halves, you get this line. Well, that line has the equation just y equals t. So because we're doing it on the positive integral, we can replace the absolute value of t with simply t. Now, if we were asked to integrate over here, like let's say the interval was negative pi halves to 0, say, just say it was, you would have to replace your absolute value of t with negative t. Okay, but we don't. All right, so now the integral of t, that's easy. You learned how to integrate t when you were in calculus 1. Fine. and then you evaluate at the upper limit first, minus the lower limit. And then what do you get? Oof, boy, I get pi squared over 4 divided by 2, minus 0. This looks like it's what, pi squared over 8? Okay, your exact answer is that yucky number. Square root of 5, pi squared over 8. That's the exact answer. And that's why I put this cartoon in there. Get it? Pi squared. Professor, I ran out of round pans. Do you mind if these pies are square? Get it? Pi squared.